Hello everyone, this is Brock Skaggs. I'm going to make this video where we're going to look at deriving the elastic curve equation or the deflection formula for the beam and loading you see before you. And so our beam and loading, fairly simple. We've got a uniformly distributed load over the simply supported beam itself. So pin connection at the left hand side and a roller at the right hand side. One thing that I haven't explicitly drawn is where the origin at and the positive x and y directions. Well, I'm thinking the origin is at the far left end of the beam at point A, and the positive x direction is pointed to the right, and the positive y direction is upward. And so I've also mapped out a solution path for us that we'll try to follow, just to give us a little more structure. And so first thing we're going to do is determine the reactions, and then we're going to find this m of x expression. And so this m of x expression is the equation, if you will, that is going to be telling us how the bending moment is changing as we walk along the length of the beam itself. The reason that we're needing to know that is because when we get down here to solving this differential equation, the governing differential equation that we'll be working with is y double prime of x is equal to m of x all over e times I. And so notice right here in this equation I have to have m of x in order to complete it. After we go from here, we'll take some integrals. We won't get into too much of the actual def-eq or ordinary differential equations portion in order to solve it, but we'll just think of, hey, I've got a second derivative here. I need to get back to the original function, so I'll just integrate a few times, and then we'll have to deal with the integration constants, which is what steps 4 and 5 are going to be with here. And so that is the plan for how we're going to attack this problem. And so let's jump right in. First thing we need to do is determine the reactions. And so the way I'm going to determine the reactions is I'll do it fairly formally, if you will, by drawing a free body diagram of the entire beam here, and then using equilibrium equations to arrive at the reaction values. And so here, let's say I'm drawing a free body diagram of the entire beam. I've got a pin connection here at the left hand side, so I'll represent that by a sub x and a sub y components of that force associated with the reaction. I've got a roller on a horizontal surface here, so we have a upward reaction force b sub y, and then what we really have is a uniformly distributed load, which I'll just draw in blue at this point, that goes over the entire length of the beam. But instead of thinking of the uniform distributed load, I'm going to think of a statically equivalent point force that is located at the centroid of the area associated with the distributed load and has a magnitude equal to that area. And so in this case, our area is just a rectangle, so it's base times height, so the lowercase w times the overall length of the beam. And as far as where I'm placing that along the length of the beam, it's going to be exactly at the middle. And so overall length is L. This will be at L over 2 units from each side. And so using this free body diagram, we can now solve for our three unknowns, a sub x, a sub y, and b sub y. And so I'll just come over here to the right and start writing our equilibrium equations. And so first thing I'm going to say is sum of the force in the x. That's going to be a sub x, which has got to go to 0. And then I can do a moment equation. I'm going to pick about point A, and I should be able to solve for the reaction b sub y. And so here I'll start left to right. I'm talking about point A, so it's right over here. A sub x and a sub y obviously go through the point, so I don't have to worry about them. Walking left to right, I have this static equivalent point load here, capital W. It's going to try to cause clockwise rotation, so it's a negative contribution to the moment equation. The force part of it is just lowercase w times L. The perpendicular distance is L over 2, that horizontal distance there. And that is the complete moment contribution for the uniformly distributed load. Again, we're going through it, the statically equivalent point load in this part of the analysis. And last but not least, we hit the far right hand side, so we've got this upward direction, and it would be causing counterclockwise rotation, so positive moment here, and it would be b sub y times L. And so here we'll have plus b sub y times L, and we'll set everything equal to 0 for our static equilibrium. Here, just by looking at it, I can divide an L out here and an L out here for our equation. And then I can solve nicely for b sub y, which is equal to WL over 2, or half the total load pushing down on the beam itself. So I still have one more unknown to find, a sub y, and so we can write a equation describing the vertical equilibrium for the forces. And so we'll say sum of the forces in the y, we'll have a sub y plus b sub y minus the capital W. I'll write it as lowercase w times L, and we'll set that equal to 0. Now I can solve for a sub y, which we can see is w times L minus b sub y. But what did we find b sub y was? A couple lines earlier we just said b sub y was WL over 2. And so now we've got the full WL minus WL over 2, which gets us to, again, WL over 2 here. Just basically 1 minus a half. This gets me to a half. And so at this point we've completed step 1. We've determined the reactions here, specifically a sub y and b sub y, each of them carrying half of the overall load on the top of the beam there, or WL over 2. One thing you'll also notice that throughout this video we're going to keep everything in variables. That way everything is much more generalized, and so that way when we arrive at a specific beam that we're wanting to analyze, it's just going to be basically plug in the specific values for L and lowercase w in order to calculate our solution, not have to go through this re-derivation for every special case. And so now that I found the reactions, I need to find m of x. And so what m of x is, again, is a description of how the internal bending moment is changing as we walk along the length of the beam. And so how we'll do that is by drawing another free body diagram. And here I'm just going to have the left boundary of my free body diagram be at the origin at point A, and the right hand side boundary I'm going to make at some general point x, where x is going to be somewhere between 0 and L. And so I guess I'll make that a little more explicit here. I'll say, let's draw the free body diagram where 0 is going to be less than x, which is going to be less than the overall length of the beam. And so just like before, we'll go ahead and draw a nice rectangle. This will represent the beam for us. And then what loads is this chunk of beam experiencing? And so here, I still have a sub y here on the left-hand side, and it'll be WL over 2. I'm not going to even draw in a sub x because we saw it was 0. At this far right end, I'm making a cut through the material of the beam itself, and so there will be a shear force and bending moment possibly here, V and M. And I'm also going to make sure that I remind myself that this cut is x units long here, where I've got the domain of x specified right here. If you want to, I can also call this point here point x for us. And so we're missing the actually externally applied load portion of this free body diagram. And so again, just remind myself, hey, this is a uniformly distributed load all the way across this beam segment. But just like in our first free body diagram, I can make this statically equivalent point load right here. Again, I'll call it capital W, but this time this capital W is just lowercase w times x here. Notice this capital W expression is different than the one above. Here, the length of the free body diagrams are different. The first one I've taken the entire length. The second one I'm just taking some length x, and hence the reason for putting w times x here to characterize the magnitude of the area under this distributed load curve. As far as where I'm placing it left to right on this section, well, it still has to be at the x-bar or centroid location for the shaded area. In this case, still, it's a rectangle, so half the base, or x over 2 units from each side here. And so I believe our free body diagram looks complete at this point, and the only thing I have left to do is to determine this m value, because from this m, I should be able to relate it to the position along the length of the beam. And so how we'll do that is by using our equilibrium equations. We have a chunk of beam now, and so if the entire beam itself is in static equilibrium, the chunk has to be in static equilibrium. And I can use the sum of the moments equation, or moment equilibrium here, in order to arrive at a relationship which will tell me how m changes as I walk along the length of the beam. So m is a function of x. And so what I'll do is draw not necessarily draw, but write my equilibrium equation. And I'm going to pick point x as the point I'm taking the moments about. And this time let's go right to left. And so the first thing I do have is m, drawn in the positive direction there. V here, V is the internal shear force at that cut section, and so it's passing right through point X, so I don't have to worry about it. And the next thing I hit is the statically equivalent point load, capital W. And so it's trying to cause counterclockwise rotation as well, so it's plus here. Instead of writing the capital W, I'll write it as lowercase w times x. That's the force part. Now the perpendicular distance, so times x over 2. And that is the moment contribution of this statically equivalent point force. And then the last thing we have at the far left is a sub y. It's pointed upward, which is going to cause clockwise rotation, so it'll be a negative moment contribution to my equation. And so the magnitude of the force is w times L over 2, and the perpendicular distance is the x units there. And so it'll be minus WL over 2 times x, and this whole thing's going to be in static equilibrium, so we set it equal to 0. And so at this point, it's just a matter of solving for m. And so here I can say m is equal to, I will write it as negative w over 2 times x squared plus WL over 2 times x. I'm just kind of getting the polynomial feel to it, so I have some coefficient times x squared plus some coefficient times x there. And so this equation here is exactly what I was after for step 2. Now I have a way that I can pass in a position x value. If I know the distributed load lowercase w, if I know the overall length of the beam L, it will immediately return to me the internal bending moment at that given spot on the beam. And so now we've got item 2 done. We're ready to jump down into item 3 here in order to solve the differential equation for our general solution. And so the general solution, what we're talking about here, is it's going to be a solution. It's going to describe a whole family of curves, and it's still going to have those arbitrary integration constants within it. And so the first thing I'm going to do is say, yes, I'm using this governing differential equation. The second derivative of the elastic curve equation that I'm looking at, basically something discussing the concavity of the beam at any given point, is equal to the bending moment expression divided by E times I. And so at this point we'll just plug in what we know. And so we've got y double prime of x is equal to, I'll write it as 1 over E times I, and then in the square brackets we need our bending moment expression. And so negative w over 2 times x squared was the first term. And I believe it was plus WL over 2 times x for our second term. Very good. And so at this point all we've done is plug in our actual expression for m of x. And so again, the idea here is we're wanting to get to the y of x. And so here we're at the second derivative. And so very loosely, if you'll let me have some very loose math notation, I'm just going to integrate once with respect to x, and if I integrate the left hand side with respect to x, I'll be at the first derivative, and now I have to integrate the right hand side, and so 1 over e times I would be pulled outside the integral here. Here we're assuming that the beam's material remains a constant all the way throughout its length. Also the beam's cross section is going to remain constant all the way throughout its length. That way both e and I are constants here. And then inside the square brackets we actually have terms that are dependent on the position, so you see all the x's there. And so it's a polynomial, so the overall rule is x to the nth goes to the x to the n plus 1 over n plus 1. And so it would be negative w over 6 times x cubed plus wl over 4 times x squared. And then we also have an integration constant. And here I will just put the integration constant on the inside of my square brackets. I believe if you would have put it on the outside and still done your algebra correctly, we would still arrive at the exact same solutions. But here I'll just put them on the inside of my square brackets. And so what this would be, if I could figure out the C1 value, would be a equation that is describing how the angle of the beam is changing as we walk along its length there. And last, we're not after that, but we're actually after the deflection. And so we have to integrate once more. And so we'll just integrate the line above here. Again, e and I are constants. They come out of the integral. Here we have this polynomial style expression to integrate on the interior of my square brackets. And so it'd be negative w over 24x to the fourth plus wl over 12 x cubed plus c1 times x plus now another integration constant c2, where I'm trying to make sure that I keep my integration constants separate, and so that way I don't just have one c value here. I need to be sure, okay, c1 is one value, c2 is a second value there. And so at this point we have arrived at the general solution for this. And so I've got all my integration taken care of. I had to integrate twice here, but the bad thing is, as a byproduct of this integration, now I've got two arbitrary integration constants, the C1 and C2 there. And so at this point we need to know something about either the slope of the beam or the deflection of the beam, and we really need two pieces of information so we can get the integration constants taken care of. And so that leads us into step 4 here, where we're going to examine the beam and loading for the boundary conditions. And so one of the easiest ways in my mind to do this is to draw a deformed shape of it. And so here we'll go ahead and draw a deformed shape, very exaggerated. And so what's going to happen is we're going to have something that looks about like this when the beam becomes deformed. Excuse where I get real thin here. That's just me trying to draw. And so what do we know about this? Well, one thing we know is the angle is going to change at the pin and the angle is going to change at the roller. It's going to start off right at horizontal, but then as this load's applied, that 90-degree angle, if you will, is going to become less there, and we don't really know what that angle is, and so we don't really have a whole lot on slope. But one thing I can say is the displacement of a couple points, and those points really are right here and right here, because I know the displacement at both the very beginning at x equals 0 and the very end at x equals L are going to be 0. That's just because of the nature of this simply supported beam itself here. And so how we say that is that we know that y at x equals 0 is equal to 0, and y at x equals L is also going to be 0. And so these would be our known boundary conditions. And what this allows us to do is solve for the integration constants up here. And so with that idea, we can now go into step 5. And so in step 4 again, what we're basically doing is we're drawing a exaggerated deformed shape of the beam, and we're looking at it and say, okay, do we know anything about either the position or the angle of the beam at any given point there? And so in this case, we do know it at the very beginning and the very end. They're both going to be 0, and so we can use those two pieces of information, those two boundary conditions, in order to solve for our integration constants. And so with that being said, let's just use the first one first. And so if I'm using the first one as y of 0 is equal to 0, what that means is the 0 on the left hand side is this y of x, so I can say 0 here is equal to, and then the first 0 here, y of 0, means that every time I see an x in this right hand side expression, I need to plug a 0 in. And so I've got 1 over e times I times, again I'm just following this line right here for the deflection, negative W over 24. Now I've got x to the fourth, so it's 0 to the fourth, plus WL over 12 times 0 cubed, plus C1 times 0 plus C2. And so I look at this. One thing I could do is multiply both sides by E and I, and that goes away. And then also all the terms here, that's going to go to 0, this is going to go to 0, this is going to go to 0. And so what that leaves me with is that C2 is going to equal 0. And so I've got one of the two integration constants determined at this point. And I've used this piece of information, that the deflection at point x equals 0 is going to equal 0. And so now we use the second one. So we'll say y at x equals L must equal 0. And so again, same idea. The 0 on the right-hand side has to do with the y of x part, so 0 here. I've got 1 over e times I. And we're just walking through the general solution part of the deflection formula here. And so 1 over e times I, and then I've got negative w over 24. Now I've got L to the fourth instead of x to the fourth, and I've got w over 12. Here I'm going to have an L from the coefficient and then L cubed, so it'll be L to the fourth again, plus C1 times L, and I'm not even going to write C2 because I know it's going to be 0 here. And so I'll square bracket that off and zoom in here so I can write a little bit better. Here I can multiply each side by e times I, so we can eliminate that. And so we have 0 is equal to a negative w over 24 L to the fourth plus w over 12 L to the fourth plus C1 times L. At this point I could divide an L across, and so this would go away. This one would be to the third power. This one would be to the third power as well. And so now just a matter of solving for that C1 value. In this case it's not going to be a 0, it's going to be some non-zero value, and I've got positive w over 24 L cubed minus w over 12 L cubed. What is 1/12 here would be the same as 2/24, so this ends up being negative w over 24 L cubed after we deal with the fractions there. And so at this point is almost time to celebrate. We've got the second integration constant determined, and so now we can write the equilibrium equation, or not, excuse me, not the equilibrium equation, but the elastic curve equation. And so at this point what we can do, just grab this work that we did before, paste it down here. In this case, I'm not going to worry so much about the slope, even though we've got the C1 value, so we could get that one fairly easily. But I'll eliminate it, and C1 times x. Now I know the C1 value, and the C1 is actually negative w over 24 L cubed times x. And then the C2 is 0, so we leave that one off. And that looks good. And so one could do some algebra here in order to distribute, say, the negative w out, and the 24, I believe, out of the denominator we could get out as well. But I'll just leave it right there for now. And so this is going to be the elastic curve equation, or the deflection formula, for a uniformly distributed load across a simply supported beam. Right up there. And so the nice thing about this is now anytime we see a beam that looks like this, as far as has the uniformly distributed load over its entire length and is simply supported, we can use this equation down here in order to tell us very quickly the amount that every point x along the length of the beam is going to deflect there. And so again, as far as the steps we went through here, 1 and 2 are basically prep steps in order to get us the internal bending moment as a function of the position along the length of the beam. Then we used the differential equation here as our basis. We did a couple integrations in order to get to the general solution for this deflection formula. To get away from the integration constants, though, we had to examine the connections of the beam as far as looking for known boundary conditions that we could use. And so we ended up using both of these conditions in order to solve for the C2 value first and then the C1 value. And so that should conclude this video. Thank you for watching it, and hopefully it helps you with your beam studies.